This is a recording from a Sunday meeting of the BC Humanist Association in Vancouver. Humanism is a progressive worldview that, without supernaturalism, affirms our ability and responsibility to lead meaningful, ethical lives capable of adding to the greater good of humanity. To learn more about humanism and to support our work, visit bchumanist.ca and make sure to follow us on Facebook, Twitter, and Instagram, and be sure to subscribe to the BC Humanist podcast. The opinions expressed in this podcast do not necessarily reflect those of our staff or board of directors.
Jaymie Matthews is a professor of physics and astronomy at UBC. He's received countless teaching awards. One award I did see that he has been awarded is the Member of the Order of Canada, which is one of the highest... Officer. One of the highest awards you can get in this country, which is pretty impressive. I've seen a couple of his talks, and they're always entertaining, as you can tell from his shirt and costumes he wears. Today he's here to tell us about the stories behind the astronomers who are responsible for our understanding of the universe. I want to just give you a brief little bit from the Amsterdam Declaration of Humanism to put that into context for today. Humanists believe the solutions for the world's problems lie in human thought and action rather than divine intervention. Humanism advocates the application of the methods of science and free inquiry to the problem of human welfare. But humanists also believe that the application of science and technology must be tempered by human values. Science gives us the means, but human values must propose the ends. So today will hopefully remind us that scientists are human too. Thank you, Jaymie Matthews.
So that's appropriate in the introduction because my topic today was really inspired by the fact that I would be speaking to the BC Humanist Association. And so I wanted to tell the human story behind the science. And later this afternoon, the 90th Academy Awards ceremony will be held in Hollywood. And in that vein, the stories behind some of the major discoveries in science, in astrophysics and in physics, would make great Hollywood screenplays and great movies. And we, I think, starting to see some of that, moving in that direction. And so I want to kind of, convince you that if there's a Hollywood movie producer out there in the audience, that I could pitch you a really good screenplay. Also, I'm in a kind of a trivia state of mind because on Friday night I hosted the first ever UBC Astronomy Club trivia night, and right after this I'll be rushing back to Kits for the weekly Sunday trivia at Sophie's Cosmic Cafe on 4th and Arbutus. I'm the resident rocket scientist who puts a little extra cosmic in the Cosmic Cafe. So speaking of trivia, I decided I wanted for this talk to create a new Trivial Pursuit category, mathematics. And here is one of those new Trivial Pursuit questions. What's the connection between calculus and life insurance? And it's also a physics Trivial Pursuit question. What's the connection between gravity and life insurance? Other than the obvious thing is that, like if you trip and fall, then you might be able to claim an insurance thing, and gravity is responsible for that. But I'm going to talk about a more fundamental connection between calculus, gravity, and life insurance. And so this is the first of 3 chapters in my What the Textbooks Don't Tell You textbook for this morning. And the first chapter is a tale of calculus, pool, and in the case of billiards, fish, and life insurance. And my story begins with this guy, Sir Isaac Newton, who lived in the 17th, 18th century. And most of you are familiar with Newton. His law of gravitation, it's the popular myth that he discovered, quote unquote, discovered gravity when he was sleeping under an apple tree and an apple fell on his head. That's not actually what happened, but there is an apple tree. He was watching apples fall from the tree in the courtyard outside his office at Cambridge University. And apples are kind of round, and we're making them think of the sun and planets, and what was causing apples to be drawn to the ground, what would keep a planet in orbit around the sun. And he came up with this equation, which is sometimes referred to as the universal law of gravitation. Now, many of the students that I teach, especially in sort of introductory elective arts courses, who go into catatonic shock if you put an equation on the board, I try to remind them that any equation can be really written out as a sentence. And in this case, between every two objects, there's an attractive force directly proportional to the masses of the objects and inversely proportional to the square of the distance between the centers of the objects. And so it's easier to write it out as a sentence if you're kind of more an English lit inclined. You can basically deal with any equation. And I used to describe equations to students as shorthand for those sentences, until I realized that even I have never actually seen anybody writing shorthand except in a movie or an old TV show where secretaries used to take dictation. And so I'm not sure whether current generations of students really relate to the concept of shorthand. And saying this as a sentence, if you're trying to impress other people, can be a death sentence. It's more of a universal law of social repulsion. But it turns out that if you can think of equations in another way, not a shorthand. Equations are scientific texting. It's basically just abbreviating that message, that sentence, into a few symbols and emojis. And so it is kind of a universal law of communication, and I found that students can relate. If they think of equations as basically a text message, they're not quite as intimidated by it. But ultimately it is an equation, and this is one of the rules for gravity. And here's the rule book for that law, the first rule book, one of the greatest publications in the history of science, even today, which is abbreviated Principia. And I'm always never sure, and sometimes we scientists never really know how to pronounce things from the 1700s, 1600s. But in this case, it works both ways. So the Latin correct pronunciation is Principia, but it turns out that people in England at the time also actually called this Principia. So you can't lose, in either way. So my story begins with this man, the author of Principia, but the hero of my tale is this guy, Sir Edmund Halley. Now, Halley is best known for this, Halley's Comet. And by the way, it's not Halley's Comet, it's Halley or Hawley. But after the 50s, when Bill Haley and the Comets became a popular rock and roll band, Haley spelled Haley, then everybody started calling it Halley's Comet. But it really is Halley or Hawley's Comet. And this is a picture of it and its last close passage in the inner solar system when it was visible by eye in 1986. Now, he's known for this comet, but not really for the right reason, because he didn't discover this comet. Normally, comets are named after their discoverer or discoverers. But he was the one that proposed that comets that had been seen at 76-year intervals in history were actually the same comet in this very elongated orbit. And he predicted its return. And it was seen in the sky when and where he predicted, but after he had died. And so posthumously, the comet was named after him. Now, Halley was like a Renaissance man of that time, just an incredible scientist, interested in so many things. He was the first person to calculate the speed of a hummingbird's wings to see whether it could fly. And he also designed, built, and tested in 1690 basically the first diving bell. And not only designed and built it, but he and 5 of his buddies basically went down 60 feet, almost 20 meters beneath the surface of the Thames River outside of London for an hour and a half in this thing. So he was also very practical. He also became the commander of a sailing ship, a British ship called a British Pink, and it's the particular name here was the Paramour, so it's the Paramour Pink, to chart the wander of the Earth's north magnetic pole. And according to records, while he was sailing the ocean, Hawley learned to, quote, curse like a sea dog, unquote. Now, this guy doesn't really look like Captain Jack Sparrow type, so it's kind of hard to imagine him cursing like a sea dog. By the way, this is Captain Jack Sparrow's family crest from the Pirates of the Caribbean movies. And no kidding, this is Isaac Newton's family crest. Yeah. And so maybe that's why the equations have so many X's in them as an honor, subtle tribute to the family of Newton. Now, Hawley wandered around the globe in the Paramour Pink, and this was the route of the Paramour. And what I'm showing you there is the cover of a great book called Halley's Quest, which talks about his adventures and the science behind that journey. And so if you're looking for and this would be another thing that would probably make a great movie, by the way, is turning Halley's Quest into a screenplay. That's the map of the route of the Paramour. Here's the map made that Hawley published in 1701 of the Earth's magnetic field as charted from all of these journeys, and in particular the variations of the field, because the Earth has this giant natural dynamo inside, like an electric motor, where the liquid iron in the core of the Earth is circulating around, carrying charges, and so it's like the coil of wire in an electric motor, except there's no wire, but currents are flowing around. And so the Earth's north and south magnetic poles do not coincide with the Earth's north and south geographic poles, and they shift over time. And Hawley was the first person to really, and his crew, to give us a detailed account of how it was shifting. Right now, the north magnetic pole is racing at the fastest speed it's ever been observed to move, about 70 kilometers per year. Moving away from Canadian territory or towards the Canadian border, towards Russian territory. But for the moment, we still own the North Magnetic Pole. Now, Hawley was also, interacted with many other people in the intellectual community. And in January of 1684, he invited architect Christopher Wren and physicist Robert Hooke over for dinner. I'm sure most of you recognize the name Christopher Wren, but if you don't, he's the guy that designed St. Paul's Cathedral in London, so not too shabby. And Robert Hooke, I know we have some physicists in the audience, they would know Hooke. His studies of the elasticity of springs led to a law being named after him, Hooke's Law. He was an avid user of the microscope. He's the one who came up with the term cell, to talk in biology. And he was also the arch nemesis of Isaac Newton. Now, nowadays, people don't tend to have an arch nemesis except for Sheldon Cooper in The Big Bang Theory. But in those days, apparently it was quite common. And I know I don't have a lot of time, but I can't resist. You may have heard the quote from Newton that everything that I have accomplished, I have done so by standing on the shoulders of giants. And it's a very noble expression. You see it, you can see it sewn into a pillow and so on. It's in posters. And it is true that every accomplishment that we make, whether it's in science or technology or in literature or in theology, are built on the accomplishments of those that went before us. However, when Newton said this, he said it to the Royal Society of London. He was speaking, and right in front of him, in the first row, center right underneath him, was Robert Hooke. And he was staring at Hooke when he said this. Hooke was a dwarf. So this was just a backhanded, stabbing in the back, but in a way in which nobody could really call him to account. So Newton was a clever guy, but to be honest, from everything I've read and studied about Newton, beyond his science, his brilliant in mathematics, not a really nice guy, not the kind of guy that I would want to have a beer with. He became the Exchequer of London, the tax collector, and he had people assassinated for being late in paying their taxes. Anyway, but Hooke and Newton had this ongoing war. But, Hooke was also, maybe not the easiest person to get along with. But at that dinner, Hooke bragged to Halley that he had derived Kepler's 3 laws of planetary motion. But he couldn't produce the derivation, and Halley was suspicious of the claim. Now, what are Kepler's 3 laws of planetary motion? Well, Kepler was Johannes Kepler, a German mathematician who had been hired as an assistant by the leading astronomer of his era and the best observer of the night sky before the era of telescopes, the Danish astronomer Tycho Brahe. And if I have time, you're going to hear a little more about Tycho Brahe in the second chapter of my trilogy this morning. And Kepler took 2 decades to correctly interpret his boss's careful measurements of the positions of Mars and other planets, which were known as wandering stars. And that's where we get the word planet, by the way, from the Greek planetos, which means wanderers, in the sky. And his 3 laws of planetary motion are still used today, not just for the planets in our solar system, not just for the moons around planets, not just around satellites around planets and moons, but stars orbiting around other stars in binary and multiple systems, and even galaxies orbiting around other galaxies and clusters. And so this is one of the most powerful tools in an astronomer's toolkit. So I want to briefly kind of give you Kepler's 3 laws. And the first law relates to the shape of an orbit. And the ancient Greeks loved geometric perfection, especially the circle and the sphere. They were convinced that all celestial bodies were attached to invisible celestial spheres moving on circular paths. So they loved circles, and so did Kepler. And he started with circles, but he had to abandon them because they just wouldn't fit the data. And that's the beauty of science, is sometimes we are dragged kicking and screaming to a place we don't want to be, but because the data, the evidence demands it. And the shape that worked better, most of us would call an oval. Mathematicians and astrophysicists would call it an ellipse. And so Kepler's first law is that all planets' orbits are ellipses with the sun at one focus. And I'm showing a more exaggerated ellipse than for the planets in our solar system. The planets in our solar system are pretty close to circles. A circle is just a special case of an ellipse, but they are elliptical. And in fact, we have discovered planets around other stars which have orbits which are even more elongated and more cigar-shaped than the one that I'm showing here. Now, if you ever want to draw an ellipse, it's actually pretty easy. You just get a couple of tacks, piece of paper, put them on a table like this, maybe put some mat down so you don't put pin marks into the table. And then you loop thread around those tacks, and then you draw, you have a pencil or a pen on the paper, and you draw a curve keeping that loop string taut as you move the pencil. And the tacks are each one focus of the ellipse. Foci is the plural. And what you're doing is reproducing the mathematical quality of an ellipse, which is the fact that if you go from one focus to any point on the ellipse to another focus, those 2 straight lines always have the same length. And so that's why you're keeping the string taut. And you will trace out pretty much a perfect ellipse without even knowing the mathematical formula for an ellipse. So I want to tell you a little bit about a mathematical detour in my life involving ellipses. When I was young, there is the equation for an ellipse, by the way, in case some of you were upset that I didn't give that. So I've wanted to be an astrophysicist since basically age 2. My earliest memories are seeing these pinpoints of light in the sky and wondering what they were. I wanted to be who and what I am today before I knew what it even meant to be who and what I am today. And so I was an uber astro geek from square one. And when I was in grade 8, my hometown of Chatham, Ontario, I came up with an idea to raise money for a school fair that we were having for charity. And what I did was in our garage, as an only child, poor family, and in the garage, I built an elliptical pool table. And so the pool table had one pocket, and then the bumper around the rim, and I would have a cue ball and an 8 ball on the table. And here is how it worked. People would come, they'd pay $1, And then they would have to hit an 8-ball with the cue ball so it bounces off of the bumper and into the pocket. And if they miss, then I have to take the shot from wherever the balls lie. And if I sink the shot, then I win. And it's pretty hard to kind of estimate how to bounce things off of a curving surface as opposed to a regular billiards table. Well, the reason why this is an elliptical table is because I knew that if the path of a billiard ball crossed or projected back over one focus of the ellipse, when it hits the bumper, it will bounce straight towards the other focus. So, of course, I put the pocket at one focus, and I didn't mark the other focus, and I knew where the other focus was because I knew the symmetry, the mathematical symmetry of the ellipse. And so I always won. Made a lot of money but I since then vowed that always to use my powers of mathematics for good and not for evil. So that's Kepler's first law. Kepler's second law is a little more complicated. A line joining the planet and the sun sweeps out equal areas in equal times. So in this diagram, what I'm showing is that from points A to B, C to D, and E to F, the planet has moved in the same amount of time to cover those distances. And now you've got these, these areas highlighted in blue, and they turn out to be exactly the same area. So the area of the AB slice is the same as CD, is the same as EF. It's kind of like if you had an elliptical pizza and you wanted to distribute the slices equally to everybody. And so you would find the focus of one of the foci of the pizza. It's an elliptical shape, and then slice it that way. And so that's kind of the pizza version of Kepler's second law. Now, what this means is that a planet's orbital speed changes depending on its distance from the sun. We call the point closest to the sun perihelion, helion referring to the sun for Helio, the Greek god. That's also, by the way, why helium has its name, because it was first discovered in the spectrum of the sun. And in the third chapter of my trilogy, I will talk a little bit about the spectrum of the sun. And the most distant point is called aphelion, or aphelion. So it's fastest when it's closest to the sun and slowest when it's furthest away. Now, in planets, it's kind of subtle because they are not extremely elliptical, but comets, like Halley's Comet, are a very good example. Here is the orbit of Halley's Comet, with different years of its location in the orbit and the orbits of the planets shown. And you can see that when Halley made its last appearance in the inner solar system, it went from basically very close to the sun to the orbit of Saturn in 3 years. But in 3 years, in 2010 to 2013, it covered a much smaller distance. Then the third law is to relate the period of an orbit and the size of the orbit. And going back to the ancient Greeks, not only did they love geometric perfection, but they loved musical harmonies. They called the planets wanderers, as I said, and they considered them the homes for wandering minstrels. And there's a quote from Plato: "A siren was sitting on each planet, caroling a most sweet song, synchronized with the motion of her own particular planet, but harmonizing with all the others." And Kepler believed, like the Greeks, that the periods of the planets were somehow related by musical harmonies or overtones, and he looked for them. They had established basically musical notes and terms for each of the planets, and here is the literal harmony of the spheres. But again, Kepler failed to find a way to relate the data to musical harmonies, and he had to reluctantly leave that. And then he searched for some simple mathematical relation between the orbital periods of the planets and the sizes. And because now planets' orbits are not circles, as they were thought, they're ellipses, the way we define the size of an ellipse is called the semi-major axis. And for a circular orbit, the semi-major axis is the radius of the circle. So what he did was, for the planets that were known at that time, there were 6, the 5 that you could see, looking up without a telescope, and the one that you could see without a telescope looking down, the one we're on, the Earth. And so here are the sizes of the orbits measured in units of astronomical units. That's the average size of the Earth's orbit, and the period in years. So everything's scaled to the Earth. So the Earth is 1 and 1 in these units. And nobody at the time knew what the absolute values of these distances were. And so then he basically looked for simple relationships. Before calculus, before calculators, he looked for a simple exponential relation between semi-major axis A and the period P, and it took him 20 years, and he finally found the answer. P squared equals A cubed if you choose the units wisely, if you use the Earth units as 1 and 1. Now, in this table, the numbers don't quite balance just because I was working on this late last night and there's rounding errors in my calculator, but trust me, it actually does work. And it works for all the other bodies orbiting around the sun, not just planets, but asteroids and Pluto, which was not known at the time, but is no longer considered officially a planet, but a dwarf planet. By the way, dwarf planet is not just another category of planet, like a smaller version of a planet as a loophole to keep Pluto in the club. You have to say dwarf planet in the same way you say hot dog. A hot dog is not a canine who needs air conditioning. A hot dog is a hot dog. And a dwarf planet is not a small planet. It's a dwarf planet. It's just not a planet. So, these were empirical laws. Kepler had figured out how the planets orbited the sun, but he didn't know why they did that. And we refer to those as empirical, based on observation, but with no physical explanation. And so we come back to that dinner in Halley's home, in which Robert Hooke had claimed that he had derived Kepler's laws of planetary motion, but could not produce the derivation for Halley. But that inspired Halley to take the problem to his friend Isaac Newton in the summer of 1684. And Newton was excited, inspired by Halley's enthusiasm and interest. And in a matter of months, Newton came back to Halley with a manuscript, De Moto Corporum in Girum, of the motions of a body in orbit, deriving Kepler's laws with Newton's new ideas of an inverse square force, a force between things that dropped off as the square of the distance. And that's the equation that I showed you before, the universal law of gravitation. Newton, Halley was so impressed by this that he pleaded with Newton to do more of it and present it to the Royal Society. And so Newton, basically, this became his obsession for years, the next 2 years, and writing what would become Principia, the greatest works in the history of science. And he started all of this because Halley inspired him to do so. But that's not the end of the story. This is the false climax. This is where you think, you're watching Lord of the Rings, Return of the King, and you think it's over in a way. There's another scene, then you think it's over, and there's another scene. Peter Jackson just doesn't know how to end a movie succinctly, and I don't know how to end talks succinctly, as you're about to find out. So I kind of go off in what seems to be a tangent here. Here's a fish, it's particularly red gurnard, as depicted in Francis Willoughby's De Historia Piscium, The History of Fishes. Now, why am I showing you something from The History of Fishes? Because the Royal Society consumed almost their entire budget in 1686 to publish this book. And it was not a bestseller. It was a commercial disaster. And so when Newton came to them to publish Principia, they had no budget to publish it. And so Halley stepped in, and he underwrote the publication of the first edition from his own funds. He's like many of you who will be making the generous donations to the BC Humanist Association at the end of this event. And in the 5th of July, 1687, Principia appeared in print, and other scientists and philosophers were able to absorb it. And the fact that it appeared as soon as it did was because of Halley. And if it hadn't been for Halley, that knowledge may have stayed hidden for years, maybe decades, at least to be broadly disseminated. And so we really have him to thank. But what about my original trivia question? What's the connection between gravity and life insurance, between calculus and life insurance? Well, the connection, Edmund Halley was in some sense the inventor of life insurance. I said that he was a very versatile and a Renaissance man. He calculated the very first actuarial table on which insurance rates are based. And he did it in this document, the title of which, An Estimate of the Degrees of the Mortality of Mankind, drawn from the curious tables of the births and funerals at the city of Breslau, now known as Wrocław in Poland, but it was sort of associated with Germany at the time, with an attempt to ascertain the price of annuities upon lives, which he published in 1693. So, my physics trivial pursuit question, what's the connection between gravity and life insurance? Edmund Halley, friend and funder of Newton and a very clever scientist in his own right. How are we doing for time? Okay, I think I can tell you all 3 chapters in this trilogy. I'm worried. I'm going to run a little bit over my hour allocation, but not too much, I think. So my next question is a question of morality. What would you do to possess the most exquisite scientific data on Earth? And so my second chapter is a tale of a duel, a nose, Mars, and murder. And so I have to go to the beginning of the Copernican revolution, when it was seriously considered that maybe the sun was at the center of the solar system. And there were others who had proposed this before, but none did it as eloquently and as thoroughly and at a time when everything else was starting to fall into place than the Polish astronomer Nikolai Copernicus. And there's images of Copernicus and a painting by the Polish painter Madał, if I remember correctly, showing basically Copernicus being inspired by the night sky and surrounded by the tools that he used to observe the sky, again, before the age of telescopes. So things like big protractors, quadrants to measure angles. And his book, De Revolutionibus Orbium Celestium, was published soon after he died, posthumously by his assistant, Rheticus. Now, the popular conception is that the church and society resisted the heliocentric theory because it demoted the Earth from its special central location in the universe, that it knocked us off our pedestal. And today we think of the center as the most important place and the preferred place to be. But that wasn't always the case. My friend and colleague, UBC English professor Dennis Danielson, whose specialty is the literature and theology of cosmology, how different societies throughout history have thought about the origin of themselves and everything. He has a different perspective, and I think he has the right perspective based on his research. He points out that in the 1500s, the center wasn't the desirable place to be, it was the bottom. It was the worst place to be. Think of Dante's Inferno, where the world's worst sink to the center of the 9 circles of hell. And normally you only see it from above, but here's a depiction of it both from above and from the side. And you can see it's a 3-dimensional thing, and you go down, the worst place to be is at the very bottom. And you can read descriptions of our location in the Earth by philosophers and so on. 1486, the Earth occupies, quote, the excrementary and filthy parts of the lower world, unquote. Even in the 1568, we are lodged here in the dirt and filth of the world, nailed and riveted to the worst and deadest part of the universe, in the lowest story of the house, and most remote from the heavenly arch. And that last part of this phrase is maybe the most important. Most remote from the heavenly arch. So Dennis Danielson argues that the church, and he backs it up with correspondence between church officials and scientists, they objected to the heliocentric theory, not because it demoted the Earth and knocked it off a pedestal, it's because it elevated the Earth to the realm of the stars, to the realm of God. And so you have to be very careful when looking back at history, scientific history or otherwise, and applying our current standards and attitudes, which seem to be natural, but in this case, it isn't. So the end result, my friend and colleague, Brother Guy Consolmagno, who is the director of the Vatican Observatory, an expert on meteorites, when asked about the church in Galileo, his immediate response is, almost everything that you've read about Galileo and the Catholic Church is wrong, but the truth doesn't make the church look any better. And that would be another story. Now, I mentioned Kepler's boss, Tycho Brahe, the supreme observer of stellar and planetary motions before the onset of telescopes. He built an observatory on the island of Wien, which was a Danish island, but they lost it to the Swedes in a war a long time ago. It's called Uraniborg, a sky castle. But not only was he an amazing astronomer, he was a party animal. In fact, there were parts of Sky Castle, Uraniborg, which were meant for the cloudy nights, where you had these kind of bacchanalian beer fests. And he loved to drink. And when he was a young man, he was in a broadsword duel as a university student with another student. What do you think two young, strapping university male students were having a duel over?
Women.
A woman, yeah. I'd like to think so. No, they were actually doing it over a mathematical equation, the solution of a mathematical equation. Tycho Brahe undoubtedly was the better mathematician, but he was not the better swordsman. And in that broadsword duel, he lost his nose. It was sliced off. And he came from a rich family, and so for public appearances and portraits, he wore a false metal nose, silver, possibly an alloy with gold in it. Then, as I said, that he was a party animal and he liked to drink heavily as well. And one account of his death, which happens in Prague, because he's pissed off everybody in Denmark, and so he has to move to Prague, and he becomes the imperial astronomer in the Austro-Hungarian Empire for Rudolf. And he's at a table, at a duke's table, and the custom of the day is that you're not supposed to leave the table until the host or hostess has finished their meal. Well, the Duke was dawdling over his meal. Tycho had been drinking most of the day, apparently, and he had an urgent need to leave the table. But being an astronomer and therefore a gentleman, he stayed until, according to some accounts, his bladder exploded. Now, medical types will tell you, and this is not an actual video of an exploding bladder, medical types will tell you that it is impossible for the human bladder to explode. But records of the day say, quote, something went awry in his nether regions, and at his funeral, his friend delivered in the eulogy this: the day on which he fell sick was October 13th. For at the dinner of an illustrious man, dining with others as a guest, Tycho suppressed his urine, which having been increased by the drawn-out assembly, so distended his bladder that, as if displaced, afterward it did not obey any more the wanting to cleanse. Now, there are two things that you could learn from this. One is that you don't want to ask this guy to speak at your funeral. And two is that he probably had, maybe an aggravated prostate condition. And so his bladder may not have exploded, but he did himself irreparable damage by not relieving himself when the pressure in his bladder called for it. By the way, this is an X-ray of this is the least disgusting picture of a human bladder that I could find on the web. Now, going back to Tycho Brahe as an astronomer, he didn't have telescopes, but he had quadrants, like these giant protractors that would be several stories high. And he measured the positions of the wandering stars, the planets and the stars, to accuracies of a 60th of a degree. That's 10 times better than the ancient Greeks were able to do, basically just visually. And so he had the best data on the positions of these wandering stars. Now, up to this time, and for the previous 15 centuries, everybody followed the model of the great Greek astronomer, mathematician, philosopher Ptolemy, in which the Earth was at the center, but in order to account for the fact that sometimes planets, the wandering stars, seem to move backwards in the sky, he had them going not just on circular orbits around the Earth, but occasionally on kind of little circular motions on those orbits called epicycles. And this, to be fair to Ptolemy, I'm not sure he thought this is what the universe was really like, but he had developed a model, a calculator, so you could predict where the planets would be to within the accuracy of the observations that the Greeks could make. And this held sway for basically 15 centuries. And then in the decades after Copernicus's book De Revolutionibus Orbium Celestia was published, then tide began to turn. And it had such a major impact on scientific thought, cultural thought, theological thought, that basically that's why we use the term revolution in the way we do, because before revolution just meant circular motion, orbital motion. But because of the impact of this book, people started to use the word revolution as meaning an overturning of thought, or in society, in politics. And it was first applied to politics in England in the 1680s to describe the overthrow of King James the Second, what was known as the Glorious Revolution. In fact, it was astrologers who first started to use revolution in this way, because I think of the astronomical connection, and so they used it as something, an overturning of events in the life of somebody whose horoscope they were casting. So the first evidence that Copernicus was right didn't appear until the advent of the telescope and observations by Galileo. Galileo didn't invent the telescope, but he was the first person we know of that figured out that you could use a telescope, like not to look at a bird in a tree or a mountain peak or peep in your neighbor's windows, but to look up at the universe. But even before then, the evidence from Copernicus's arguments and so on was people were swayed. And even Tycho was swayed, but the problem was like the ancient Greeks, he couldn't measure something called parallax. The fact that if the Earth was moving around the sun, our perspective on the stars should change. We should see them kind of from different angles. And nobody saw that. The Greeks didn't see, ancient Greeks, neither did Tycho. The problem is nobody realized how far away the stars were. The largest shift in angle for the nearest star is about 1/4000th of a degree due to the Earth's motion around the sun. And Tycho Brahe could measure angles to 1/60th of a degree. This parallax effect was not measured for the first time until 1871, I believe. But he did recognize that the planets must orbit the sun. And so he had a modification to the geocentric universe. The idea of the geocentric universe is that we were at the center of the universe and everything revolved around us. We sometimes now just call that Donald Trump. And so he came up with the Tychonian model, in which the Earth was at the center, the sun revolved around the Earth, and everything else revolved around the sun except for the Earth's moon. But his assistant, Johannes Kepler, was not convinced. And so after Tycho's death, Kepler inherited the data, the observations, and he spent 20 years figuring them out and coming up with his laws of planetary motion. Now, a few years ago, about 17 years ago, a husband and wife team of journalists and authors, Joshua and Annalee Gilder from Seattle, published a book called Heavenly Intrigue, in which they presented evidence that Kepler actually killed Tycho Brahe, because Brahe was very protective of his data, and it was only coming out in dribs and drabs, and Kepler couldn't wait to get his hands on those data. And they argued that Kepler was so impatient that he assassinated his boss in order to get the data. Now, the death happened in Prague, as I said, and in fact there's a tomb in the Old Tin Church, in the Old Tin Square in Prague. You can visit, and there's an eternal flame, and there's a brass relief of Tycho Brahe there. The Czechs did it up right for Tycho Brahe. But a few years ago, and in fact, what inspired this book was that follicles of Tycho Brahe's beard were exhumed from the tomb. and analyzed by Danish scientists. And here's the chemical analysis of the follicles. And this plot, thanks to Jan Pallen from Lund University in Denmark, this is basically showing as your hair is growing, it's kind of like the rings in a tree trunk, but linear. It's keeping track of the substances that you've ingested are being partially deposited in your hair follicle. And so as the hair grows, you get different concentrations depending on the things that you've eaten or drank. And basically, they found, and based on the rate at which the hair grows, you can translate that into time. And according to Pallen's group, they found a peak, a high concentration of mercury ingested 13 hours before Tycho Brahe died. And the prime suspect, apparently, at least in this cold case, was Johannes Kepler. Now, if they had kind of interviewed his neighbors at the time, they would have said he was a quiet man, and he was very serious, completely opposite in personality to his boss, except for their passion for astronomy and science. And so there's really no historical evidence that Kepler was capable of murder, that he had that kind of temperament, but human beings can be unpredictable for better and for worse, as we know. So it's hard to maybe make that case. But fortunately, for Kepler's reputation at least, Tycho's body was exhumed again 5 years ago. Closer to 4 years ago. And fuller analyses were done of bones and hair, 3 different independent analyses that all came to the same conclusion. The mercury concentrations were not high enough to be fatal, and he wasn't exposed to abnormally high loads of mercury or anything else in the last 5 to 10 years of his life. That's a surprise, actually, because Tycho was also an alchemist. And alchemists tended to work with a lot of mercury, like hatters. That's where we get Mad Hatter, because the breathing in mercury fumes can have a deleterious effect on your mental state. So I'm kind of surprised that he didn't show abnormally high loads of mercury in the last decade of his life, because I would have expected that. So I think it's safe to say that Kepler has been found not guilty. But the question of morality still, I think it is basically a case study of what would you do to possess something really valuable in terms of scientific data. And one possibility that journalists thought about for a while was to go Kepler on your boss. And now, I think I'm doing okay for time. One final question. What are the stars made of? That's a dangling participle, so don't learn English grammar from me, just learn astrophysics from me. Of what are the stars made? And that inspires the 3rd chapter in my trilogy, which is a tale of light, a harem, a heroine, hydrogen, kitten mittens, and the Ottawa Senators. So follow along and keep track of where all of these things come up, because they're all there. So my question is, what are the stars made of? Another question is, what makes a rainbow? And most of you, I think, know that, at least in the basic principle. Water droplets suspended in the air after it rains will bend and partially reflect sunlight. They act like spherical lenses in the sky. And the bending angle of the light depends on the wavelength, the color of the light. And so raindrops spread the white light of the sun into a spectrum. And here's actually a relatively rare sight, a double rainbow. The geometry will produce 2 arcs, but the outer arc is usually too faint to be seen, so there it is. And the water droplets don't have to be suspended in the air. There's a little water droplet on a blade of grass, and you can see it spreading out the light into a rainbow as well. Now, astronomers produce rainbows from sunlight and starlight, but a much finer rainbow in an instrument called a spectrograph, where you will still see the colors of the spectrum if you're looking by eye or in a color image, but imposed on that band of colors from violet to red are these dark lines, which we call absorption lines. And they are the fingerprints the barcode of the atoms and molecules and ions that are in the gas at the surface of the sun or of another star. And we can generate those in the lab here on Earth, so we can see the fingerprint of, for example, helium, sodium, neon, hydrogen, and so on. In this case, they're made to glow in a tube where it's kind of like a neon sign where you put in electrical energy and you make the atoms and the molecules give off light at particular wavelengths as opposed to absorbing light, which is what's happening in the sun. And here are the rainbows, if you will, of different types of stars ordered in temperature. So going from coolest at the bottom to hottest at the top. And you see they all have that rainbow continuum, but then they have different sets of fingerprints, different barcodes, depending on what. And the barcodes get really complicated when you get to the coolest stars because they're cool enough now that you can have molecules in the atmosphere. And now they just don't make like sharp, narrow absorption lines in the spectrum. They make what we call molecular bands in there. And the strengths of the lines depend on the star's temperature, the temperature of the gas at the surface. Now, originally, more than about 100 years ago and more, astronomers, once they were able to build spectrographs and had cameras with photographic emulsions to take pictures of the spectra, they took spectra of lots and lots of stars, black and white images, because you didn't have color then, and usually negatives. You worked with the negatives, so now that bright rainbow background is just black, and the absorption lines show up as bright. And they just sorted everything in terms of the strengths, the depths, the blackness of the hydrogen lines. And they sorted them alphabetically from A to O, strongest lines to weakest lines. So they just dropped them into bins from the Harvard Observatory. And during World War I, Edward Pickering, who was director of the Harvard College Observatory, hired women to serve as computers. Now, when we say computer today, we think of something like this. But computer used to be a job description. A person who was a computer was a person who did calculations for a living or were paid to do calculations. And this was the first computer cluster. He hired women to analyze the data from his survey of stars of the Milky Way by classifying the spectra recorded at the Harvard Observatory. How many of you have seen the movie Hidden Figures? Yeah, a number of you. So that was, it's telling a true story of a computer cluster of black women who worked for NASA in the early 60s and were vital to the early, putting Alan Shepard and particularly John Glenn into orbit, the first American into orbit. Well, this is the same story, but like 50 years earlier. And this is another story that would be deserving of being made a movie. The reason Pickering hired them as assistants is they were trained, they were highly educated, but they weren't allowed by law to work as scientists. His colleagues, all men of course, derisively dubbed this team Pickering's harem, Pickering's harem. That's where the harem in my title for this tale comes from. But these women were incredible. Talented, patient classifiers of thousands of stellar spectra, tiny little streaks on pieces of glass that they had to examine, essentially like with microscopes. And among them was Annie Jump Cannon, who in herself was just incredible. She personally classified over 250,000 of these. And that's the kind of thing that now not as a negative, but as a positive image. So on pieces of glass like that, every one of those streaks is a spectrum of a star. It's been spread out. And she would look at it basically kind of with a microscope eyepiece and identify the patterns and classify them. And she did that for more than 250,000 of those little streaks. Now, you would have thought that would have just driven her crazy with boredom, but she knew how important it was and how exciting it was because they were learning about the nature of stars. And so this was her Christmas card in 1915, the story of starlight, describing to her friends and family what she was doing at the Harvard College Observatory. And that was her kind of Christmas gift, the gift of knowledge and excitement about learning about the universe. And she recognized that the strengths of the star's hydrogen absorption lines behaved in a more complex way than the Harvard astronomers had thought. And so she revised the original alphabetical classification and eliminated most of the alphabetical categories in a way that it would depend on the temperature of the stars inferred from the colors of the light. And so basically, A, B, C, D, E, F, G, H, I, J, K, L, M, N, O became O, B, A, F, G, K, M, going from hot to cooler stars. And notice, like O and M are almost next to each other alphabetically. The physics of these barcodes and spectra, very hot stars and very cool stars have very weak hydrogen lines because of the underlying physics, and I'll come to that without going into the details too much near the climax of my story. Now, generations of mostly male astronomy students, including me, memorize this sequence with the mnemonic memory aid, "Oh, be a fine girl, kiss me." Now, fortunately, we have more and more women in astronomy and astrophysics, but even "Oh, be a fine guy, kiss me" is a pretty lame mnemonic. And we've added letters since then, classifications for failed stars that are even cooler than an M star that we call brown dwarfs. And so there are letters like L and T that have been added. So in a course, a first-year introductory course that I teach for science students, Astronomy 102, on their midterm test, I want to test whether they remember O, B, A, F, G, K, M. But I want to have some fun with it, so what I do on the test is to ask them to compose a mnemonic that helps you remember, the star's stellar spectral classification sequence. And if they just write O, B, A, F, G, K, M, they'll get 1.5, they'll get most of the marks. But I want them to write something. And then basically I give out awards. And I mentioned that the Academy Awards are tonight, so it's appropriate. I will have the presentation of the Academy of Stellar Spectral Classification Mnemonic Awards, which I've nicknamed the Annies, after Annie Jump Cannon. And so the winners are, may I have the envelope, please? Somebody has an envelope? You're supposed to have an envelope. All right, we're going to go for third prize. It's we're combining the Oscars and the Olympics. So who owns the podium? We'll start with the bronze medalist. And the third prize over the last few years goes to Aromi Lee. "Oh, bats and flowers gave Korea mighty lightning thieves." So students could include the LT for brown dwarfs, so they didn't have to. Some of them just did OBAFGKM, and some did OBAFGKM LT. And so I liked that one. That's a real photograph, by the way, of lightning on the horizon in Australia. And there's actually a comet that's poking its way somewhere into the picture, but you can't see it. Second place, the silver medal on the podium, is "Ostrich babies are fairly good kangaroo mothers, lovable and trusting," from Jinzhou. What's that? Yeah, that's my typo. I told you before, you learn astrophysics from me, not English, okay? And so what you're telling me is I have to go back and deduct a mark from Jinzhou's because she misspelled ostrich there. All right, tough crowd. I'm going to work on this before I go to Vegas. And the gold medal winner is Tegan Nevison. So I like the mnemonics that are like a sentence that has some logical form. It may not, the context may be there, but it actually kind of has a narrative flow. This one doesn't, but it just kind of rolls off the tongue so nicely. "Oh, by Abraham Flanagan's Giddy Kitten Mittens." Now, if you go on the web and look for Abraham Flanagan, you find Abraham Flanagan, and this is the correct spelling of this Abraham Flanagan. It's with an I instead of an A. He was best man at Zach and Tiffany's wedding, whoever they are. The message is that you never know where the stuff that you put on the web and social media is going to end up. So I'm sure that Zach and Tiffany and Abraham Flanagan never imagined that the picture from their wedding would appear at a talk for the BC Humanists Association in Vancouver. And if you look for kitten mittens, you get this video. And wait for it. Oh! This is actually a scene from a television show called It's Always Sunny in Philadelphia. All right, so getting back to the fact that we can use the spectra of the sun and stars and planets, this tool of spectroscopy, to actually tell us the recipes of what they are made of. And that's at the heart of the story. And so in order to introduce this part of the story, I'm going to quote from Jaymie Matthews, Dean of Arts and Sciences at Harvard, talk that he gave in February of 2002. Dean Matthews unfortunately passed away a few years ago. But he says, every high school student knows that Newton discovered gravity, Darwin discovered evolution, even that Einstein discovered relativity. But when it comes to the composition of the universe, the textbooks simply say that the most prevalent element in the universe is hydrogen. And no one ever wonders how we know. And that's true. So I want to take you back in time now, not like cosmic time. I want to go back to the world in 1927. And in 1927, that was the year of the first transatlantic telephone call. Canadian Prime Minister William Lionel Mackenzie King called British Prime Minister Stanley Baldwin. So Canadian colonists, yay. First solo non-stop transatlantic flight by Charles Lindbergh in the Spirit of St. Louis. 1927 was the year that the Earth's population of humans reached 2 billion for the first time. It was the year before women were granted the right to vote in the United Kingdom. It was the year before sliced bread was sold for the first time. You know that expression, the best thing since sliced bread? I thought like sliced bread went back like hundreds of years, and it only goes back to 1928. So what did people say before 1928 for the best thing before? And to show you how far back I'm going back in time, 1927 was the last time that the Ottawa Senators won the Stanley Cup. And that's where the Ottawa Senators enter into the title of my story. Now, what was the universe like in 1927? Well, the universe is pretty much the same as it is in 2018. A century is just a blink of the eye in the lifetime of the cosmos. But how did astronomers and scientists perceive the universe in 1927? They had only just come to realize that our Milky Way was not the whole universe, that there were other galaxies like our other Milky Way, island universes, based on Edwin Hubble's observations of a pulsating star in the Andromeda galaxy. Scientists had still not figured out what made the sun and other stars shine. This was a long-standing mystery. A fellow named Sir Arthur Eddington in the early 30s finally kind of proposed a clue. But in 1927, nobody really knew what made the sun shine, what made sunshine. And everybody believed that the sun and the stars, the universe, was made almost entirely of iron. And to be honest, this was based on reasonable observations, reasonable interpretations at that point in scientific history. The average density of the Earth was known to be about 5.5 grams per cubic centimeter. So basically, geologists knew that the center of the Earth had to be dominated by heavy elements like iron and nickel. Pieces of the solar system, samples of the universe that fell to Earth in the form of meteorites, were often found to be made of almost solid iron and nickel. And if you looked at the barcode of the rainbow, the fingerprints of the elements and in the gas from the sun and other stars, it was dominated by thousands of lines of iron and other heavy elements, not of hydrogen or helium. And the reason people had thought of iron is because they were misreading the solar barcode. So like if you take it through the checkout, if you read it correctly, you'll figure out what the product is. And it had been misscanned by astronomers and physicists until 1927. And this iron universe was not defeated by a Marvel superhero Iron Man, but by a very clever woman with steely resolve, Cecilia Payne, who later married a Russian astronomer and became Cecilia Payne-Gaposchkin. As a young girl in England, Cecilia was first inspired to pursue astronomy when she saw a meteor flash across the sky one night, a falling star. She was not a falling star. She was a rising star. At Cambridge, she studied botany, physics, and chemistry, now a Renaissance woman. And she moved to the United States to pursue her studies at Radcliffe College, say that 3 times fast, Radcliffe College, a coordinate college of Harvard University. Now I should point out, coordinate college is polite terminology. Women were not allowed to study on and live on the Harvard University campus, so this was the women's ghetto for Harvard. But for her PhD in 1927 doctoral dissertation, which was the first in astronomy at Harvard, because, by the way, it was illegal for a woman to get a PhD in physics at Harvard. And her supervisor and her mentors and instructors knew how brilliant she was, so they created a loophole. They created the Department of Astronomy, which had not existed before, because there was nothing in the bylaws that said that you couldn't give a woman a PhD in astronomy. And that department has gone on to be one of the leading research and education centers in astronomy and astrophysics in the world, almost as good as the one we have at UBC. And so the title doesn't look very interesting, but in it, she was the first person to apply the correct physics to interpret the features in the sun's barcode in its spectrum. And here is some of the correct physics, and I won't bore you with a lot of it. I could go pages and pages and pages. But what she found was that the sun and the stars, despite the different patterns in the barcodes, despite the fact that it looked like they should be in bins alphabetically from A to O, that they were made almost entirely of the same thing, and that the same things were mostly hydrogen and helium, and only about 2% of everything else in the periodic table, including iron. Nobody believed her. Her supervisor, Harlow Shapley, who is the leading American astronomer, one of the top astronomers in the world, wanted her to take it out of her thesis, and she fought to keep it in. Imagine, even today it's kind of hard. We have some people who have graduated, postgraduate students here, how hard it is to argue with your supervisor. Imagine in 1927 as a woman arguing with one of the most influential astronomers on Earth, but she got her way, and it stayed in her thesis in chapter 6. And she was inclined to say that she was wrong because everybody that she respected told her it was wrong, but she couldn't figure out what was wrong with it, and nobody could tell her what was wrong with it. And within 2 years, everybody was on board. In fact, her own supervisor published a paper on how the sun was made up of hydrogen and helium, never referring to Cecilia Payne once in the paper. To be fair, it was a different technique he used, but still. And so it's kind of revisionist history. Like, her name just got lost. Like, she's the one that showed us not just what the stars and the sun were made of, but that there was this uniform composition in the entire observable universe. That's a really fundamental thing. And so we should know Cecilia Payne's name in the same way that we know Newton's name, that we know Einstein, that we know Darwin, and we don't. And so that quote from the talk that I said from the Dean of Arts and Science at Harvard, that was part of his speech at a long belated ceremony to put Cecilia Payne Gaposchkin's portrait on the Harvard Wall of Honor in 2002. Now, you would have thought that Cecilia would have been kind of bitter because of this, but no, she was an enthusiastic. She became, by the way, the first female professor at Harvard. And so she was a pioneer in many ways. And she wrote an autobiography, which I can highly recommend for you to read. And here is something that I love. She wrote, "The reward of the young scientist is the emotional thrill of being the first person in history of the world to see something or to understand something. Nothing can compare with that experience." And for people like me who have been at it for a while, the reward of the old scientist is the sense of having seen a vague sketch grow into a masterly landscape. And I couldn't think of a better way for the closing paragraphs of my third chapter in this trilogy. I have run a bit over time. I know that we have to be out of here by noon, a hard limit. But if there is time for a few questions, these are examples of interviews that I've done on television, some by Skype. The ones at the upper left and lower right are not in a nightclub. They're in my hotel rooms in Vienna and I think Santiago. I just happen to have a portable laser light show that I sometimes travel with me and thought it would be a good backdrop, and the anchors do it. The one on the upper right is an interview where I was caught off guard for a live interview by Skype, and my webcam came active while I was eating gyoza and noodles naked in front of it and going live on CBC national television in like 1 minute. So I ducked beneath the camera, put on that t-shirt, which you see, but I'm not wearing anything but that t-shirt in that interview. So I promise I'll keep my clothes on for this interview. Thank you so much for coming out this morning and for being such a patient and attentive audience.